Hello guys, welcome to YouLearn. This is our first video, Introduction to Programming, Human versus Computer World. Now, a lot of people when they go into programming, they start with some high level language like C, C++, Java. This video mainly focuses upon what happens after you write that program. After you have written the code, you have compiled the code, what happens during its execution, how it gets executed by the CPU of the machine on which you're operating. So let's start with a very basic question about software and hardware. Now, software is nothing but a set of instructions to be executed. Now, this could be a very big software. For example, operating system, it's like a very, very big software and complicated software. Or it could be a simple program like doing addition of two numbers or printing hello world. Now, the question would be you've written the instructions, but who execute them? So, hardware is the guy who execute those instructions for you, and it's electronic circuits which we call as hardware in this context. Now, this is very similar to how people work in the real world. There is an employer, there is an employee. Employee gives a set of instructions to the employee, which is executed by the employee. Here we have replaced the employee by the computer hardware, which does the execution part for you. Now, the next question would be how the software and hardware are interlinked together and how they work together to process the instructions which are being written by you to give you the final result or the final output. So we need to understand about how can we interact with the hardware, right? I mean, this is the most important problem to solve. If you are an employer and you want to give instructions to your employee, then you need a language in which you can communicate that instructions to the employee. Similarly, since we want to write some instruction that a hardware can execute, the first thing which we need to do is define a language that is understandable by the hardware or the electronic circuits. Once we have defined the language, the second thing is writing the instructions in that particular language, right? Now, when you've written the instruction in that particular language, the hardware needs to read those instructions from particular memory location, and that's where your RAM memory or your hard drive comes into picture. You store your instructions there, and you somehow make your CPU read those instructions and finally execute those instructions to give you the final result. So this video will focus upon that, and we'll go through the steps about how did we define the language, and then how did we wrote the instructions, how we enable the CPU to read our instructions and then execute the instructions finally. So the first step, as we mentioned, is defining a language. Now, the complex part here is that you are not dealing with another human being, you're dealing with a computer machine, a hardware. So you need to define a language that is understandable by a computer hardware. Now, the first question which you need to answer for that is the language that could be used to communicate with a machine. And what does a machine understands? If you have electrical components like capacitor and transistors, they react upon only a single thing, and that is electrical current. So an electrical instrument understands electric currents. Now, can we use electric currents to communicate? Can we give some kind of signals to an electrical instruments using electric currents? And the answer is yes, we can give that. And how do we give that is by having two alphabets in our language, that is electric current on and electric current off. So just like English language has 26 alphabets in it from A to Z, our language will just have two alphabets in it, on and off. And how do we use that to communicate with hardware is what we're going to see in the next few slides. So now that we have defined the language consisting of electrical current on and off, the language can be told as a binary language consisting of two values, 0 low voltage and 1 high voltage. 0 and 1 are normally used for human representation of how the instructions are stored, and the numbers or the English alphabets are stored inside the computer. Now each of this is called as a bit. So a bit can take either 0 or 1 at its values, which is equivalent to low current and high current in computer systems. Now, if you talk about instructions, they can define by as a series of bits. So if you have four basic mathematical instructions like add, subtract, divide, and multiply, you can encode it to be 00011011. What does this mean? Is that if you have a circuit which can perform all these four operations, you can give it the signal to perform the operation by passing this type of electrical currents to it. So let's say that electric circuit has two wires attached to it. If you pass low current in both the wires, that is, you do not pass the current at all, that electrical circuit can be activated to perform addition. Similarly, if you pass currents, high currents in both the wires, it could be activated to do multiplication.
Now the next statement says the same. The circuits are designed to understand that when they receive two low voltages, they need to perform addition operation. Now let's take an example and move forward in this complete workflow. So let's say we want to execute an instruction to add two values, 1 and 2. So the resultant should be 3. So the instruction would look something like this: add 1, 2 in the human readable interpretation. If we go by the encoding logic which we have seen in the previous slide, add will be represented as 0, 0. Now value 1 will be represented as 0, 1 and value 2 as 1, 0. Now this representation of mathematical values 1 and 2 is actually the decimal to binary conversion which is being followed. So for that you can look over internet and in the link given below to understand how decimal values which we normally use in our calculations gets converted into binary and how binary can be converted back to the decimal values. So if we write add as 0, 0, 1 as 0, 1 and 2 and 1, 0, then this instruction of add 1, 2 can be actually written as 0, 0, 0, 1, 1, 0. So these are nothing but a stream of bits which can be stored in your computer and can be executed by CPU, and now you have actually written an instruction in this particular format. So let's see, now that you have actually written an instruction in a binary format, let's see how we can actually write that instruction into our hard drive and how can the CPU read it to execute it in the future. So what is hard drive? I mean, in the very simplistic definition, consider hard drive to nothing but a metal piece, right? With multiple tiny blocks in it, which are C-shaped piece of highly magnetized materials. So you can get a representation here of hard drive which has some blocks to it and they are marked by L. Now L here means that the magnetized material does not contain any magnetic field in it. It contains low magnetic field in it, right? So let's assume that this is the initial state of hard drive where all the blocks have low magnetic field in it. Mind you, they are highly magnetized material. So if you give some current to it, if you pass some current to it, you can actually create a high magnetic field in each of these blocks. Now, to write the instruction, we have something called as head. Now, head can be considered as a needle kind of a thing, which is made of highly magnetized metal and wrapped in an electrical coil. So consider it as a needle made of metallic pieces and wrapped in an electrical coil, which you can move around the metal piece which we have seen in the previous slides, consisting of multiple blocks. So you can move this head to a particular block in that metallic piece. So let's say if you want to write 1, which is the bit 1 into a particular block, you move the head to that particular block and pass the electrical current through the electrical coil wrapped around the head. As soon as you pass the electrical current through the electrical coil, the current activates the block. Remember, the block was itself made of highly magnetized material. It activates the block and create a high magnetic field inside that particular block. So high magnetic field inside a block can be considered to be 1, low magnetic field can be considered to be 0. Thus, the instruction which we had seen before, which is add 1, 2, represented in binary as 0, 0, 0, 1, 1, 0, would now be written as follows: L, 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 H, H, L. So which means that the first three blocks have low magnetic field, the next two block has high magnetic field, and the last block again has low magnetic field. So now that we have successfully written the instruction into the metallic piece, which we have called as hard drive, let's see how can your computer system, how can your CPU read this instruction and execute it through its electronic circuits. To read the instruction, we need some mechanism so that these magnetic fields can be converted into electrical currents that can go into electronic circuits of CPU. Now, the analogy here is with the eyes which work for humans. You read something through your eyes and it is processed by your brain. Similarly, we need a mechanism to read these bits so that it can be processed by electronic circuits. To read also, similar to what we have done with the write, the head will be used. Now, previously there was electrical current passed to the head that created high magnetic field inside the block. Now, whenever the head moves to a block which has a high magnetic field, the concentration in the field increases and it itself generates a current that passes through the coil to the electrical circuits in the CPU. So initially electric current was passed which created this high magnetic field. Now when the head moves through the high magnetic field, the magnetic energy gets converted into electrical energy and it passes through the electrical coil to the CPU system. To go ahead with the reading the instruction, let's assume the head starts moving from the leftmost bit to the rightmost bit sequentially. So, as it is moving from one block to another, if it's a low magnetic field, there is no current generated. If there is a high magnetic field, a current is getting generated. Now, when a current is getting generated to the electronic circuit, it will mean operation 1, otherwise it would mean 0, right? Now, let's assume you have actually created a circuit which looks something like this. It has 4 buyers incoming to it. The first two buyers are operation bit 1 and operation bit 2. So these two wires combined tell us what operation to perform. As you would have noticed, we have 4 operations: addition, subtraction, multiplication and division, and all of them were encoded into 2 bits format. 00 for addition, which is the use case we have here. Now you have a wire coming as operand 1 and another wire coming as operand 2. Now these are nothing but the two operands, which is mathematical value 1 and 2, which we want to operate. Now please note that mathematical value 1 was represented in binary as 0 1 and 2 was represented as 1 0. Now since it is just single wire for both the operands, the rightmost bit will be sent first, then it would move to leftmost bit. So this circuit will be executed twice because our operands have 2 bits inside it. One mathematical value 1 is represented as 0 1 and 2 as 1 0. So the first bits of both the operands will be passed, then the second bits will be passed, and finally the result will get as an output, which will be written back into your hard drive and will be shown on the screen to the customers. So we are now executing the instruction. So the circuit needs to execute the instruction. So we have this example of add 1 2, which is represented by 000110. So the circuit will be executed twice, as I was saying. For the addition of the first bits, which is the rightmost bit, which is 1 and 0, it will be executed something like this, where operation bit 1 and operation bit 2 are 0 0, which is addition. Operand 1, which is the mathematical value 1, has 1 as its rightmost bit, and operand 2, which is mathematical value 2, has 0 as its rightmost bit. And this circuit will operate upon it. It will know that because it has received 2 zeros in the operation bits, it needs to perform addition, and it performs addition and returns 1 as the result. After this has been returned, the circuit will be executed the second time, where the operation bits will remain the same but the operand bits will change. Now first operand bit is 0 and the second operand bit become 1. Final result is 1. So you got 2 bits as an output, 1 1. So the final result is 1 1, and 1 1 in binary is equivalent to 3 in decimal. So this 1 1 will actually get stored back into iDrive as 2 highly magnetized blocks, and when it is shown to the user, it is shown as 3, which is the decimal converted format of 1 1. So now let's see how this circuit which we had written expands to get an idea about how they actually operate among one another. So let's say this circuit actually has one component called as multiplexer and then four components which belong to the four operations: adder, multiplier, divider, subtractor. Now the job of multiplexer is actually it receives 2 bits as an input and has four output wires to it. Now depending upon the 2 bits which is raised as input, it will activate one of the output wires. So for example, if it receives 00 as its input bits, for the adder wire, it will send a current which is 1. For multiplier, divider and subtractor, it will not send any current. So it is sending 0 bits to that. And these adders or multipliers or dividers or subtractors, they get activated by this incoming bit from multiplexer. So if they get a high current from multiplexer, then they get activated and they perform the operation and return the result back. So since we had passed 0 0, the multiplexer will actually activate the adder, and as you can see, operand 1 and operand 2 both are incoming to all the four components, four operation. Since adder is getting activated, it will operate upon the two operands and result back the output. So this is how it works. Now I'm not going to explain in deep about how the adder is built or multiplier is built. Please look at the links given below to understand how they're built further. But this is the overall picture where the result is stored back exactly the same way as we have thought about initially, where it is sent as a high current, the result, or low current, and it creates some magnetic blocks inside the hard drive. Now, as we have seen how the instructions are converted into binary format, how they're stored in the computer system, how they're executed, and how their result are written back to the output stream, let's see where our programming language comes into picture, right? So, as you have seen previously, to directly interact with a machine, we need to interact with it in binary format. Now, that might be easy for simple instructions like addition, multiplication, subtraction, but to write some complex piece of code where you perform a lot many operation, you took input from humans, you perform operation, you produce output, you do all kind of graph logic and list logic. It's very difficult to write such big code in purely binary format. So the first language, right, and which people normally use would be the binary language, which is just the language which connects you directly with the computer system. So let's see how the language progress as we go forward. So a language is actually a combination of two things. It has grammar and vocabulary. Grammar in the sense, how do you construct? For example, in our use case, we had constructed operation first, first operand, and then second operator. Add 1, 2. So that is the grammar of a language, how the instruction needs to be constructed. And then vocabulary are kind of words or the instructions, which are represented in that particular language. The most basic language is machine language, which is nothing but the binary language, and you can write instruction in bits. But as I mentioned, it would get very difficult when you start writing very complex language. So this is called as low level language. Now, as we move forward, the next language which you could look at is assembly language. Assembly language is also a low level language, but you do not need to write the instruction directly in bits. It will be mostly like closer to machine instructions, like add memory 1, memory 2. So what it says is when it gets divided into bits instruction, load the data from memory 1, load the data from memory 2, add memory 1 data with memory 2 data to give a resultant output and store it in memory 3 location. Now the conversion from the assembly language instruction which we see here, add mem1 mem2, to the binary language instructions which we had seen work directly with the computer system is done by a software called as assembler. So you write instructions in its format, you run assembler on it, you get the output which you cannot understand obviously because it's written in bits and byte streams, but that output can be directly executed by the computer system. Now, as you could understand, even writing this kind of syntactical languages are very difficult to execute. So we come up with more high level languages like C, C++, Java. Now these languages have their own libraries, have their own grammar, have their own functionalities, and they define certain ways in which you need to write the code. And they say that if you write the code in this particular fashion, this will happen. So they define the grammar and vocabulary accordingly. What you need to understand is that whatever you're writing in this high level language, there would be a compiler or an interpreter. So compiler in case of C, C++, interpreter in case of Java. Now what does this compiler do is convert your code into the machine language, which is the bits language, and store it inside your computer so that you can execute it. Now there is a slight difference between compiler and interpreter. Compiler creates that byte code or creates the output in the bits format so that you can execute it, and interpreter is mostly like it executes directly. It interprets your, it generates a sort of mid-level kind of a language code, and it executes that while converting it at the runtime. So this is how the high level languages came into picture, which allows you to be more comfortable in writing complex code and complex instruction, and not concern yourself with how they'll be represented in the final bits format. So thank you guys, that's all for this particular video. If you have any questions and comments, please paste it below, and do subscribe for more videos. And this is the first video, so there might be a bit of improvement that could be made further. So please suggest whatever improvements you have in mind, or if you want to expand the content of this video. Thanks for all your help.